Here's a tricky empirical formula problem. 1.5 gram sample of a compound composed of carbon, hydrogen, and oxygen is combusted completely. These are the products. Determine the empirical formula of the compound, and if the molar mass is this, determine the molecular formula. So recall that the empirical formula of something is just kind of the representation, the simplest whole number sort of ratio of atoms of sort of each element in a compound. So if I have something like glucose, let's say C6H12O6, the empirical formula for this would just be CH2O, right? It's just like the simplest sort of whole number ratio in your compound, right? Simplest whole number ratio for each element, right? Notice how we simplified each element, right, in the individual compound. It's sort of like if we took this, I know it's cursed, but imagine if we divide it by 6, right? So 6 divided by 6, 1, 12 divided by 6 is 2, 6 divided by 6 is 1, right? And the molecular formula is just the actual like thing. So this would be the molecular formula, right? It's the actual sort of molecule. The empirical formula, you can think about it as like the simplified version. Well, first of all, what I'm going to start by is I'm going to convert these values into moles. So I know that I have 3.30 grams of CO2. How many moles of CO2 do I have here? Well, the molar mass for CO2 is around 44 grams for every 1 mole of CO2. So putting this into your calculator, so 3.3 divided by 44, you're going to get 0.075 moles of CO2. Look, I started out with a compound composed of carbon, hydrogen, and oxygen. So I have a compound that has carbon, hydrogen, and oxygen. I don't know how much of each element I have, but I do know that it has carbon, hydrogen, and oxygen. Whatever carbon that I've lost is going to be the same amount of carbon that I gained from my products, right? Because of the law of conservation of mass, right? Whatever carbon that reacted is going to be the same amount of carbon that gets formed, right? So if I have 0.075 moles of CO2, I'm going to say that for every mole of CO2 that I have 1 mole of carbon, right? 1 mole of carbon, because, right, here's a carbon, right? I have 1 mole of carbon for every mole of CO2 that I have. So doing this, I just get 0.075 moles of carbon. And also, notice how in 1 mole of water that I have 2 moles of hydrogen, right? If 1 mole of water, I'm gonna have 2 times the amount of hydrogen, right? I have 2 moles of hydrogen there. So doing the calculation, 1.35 divided by 18 times 2. So this is gonna come out to 0.15 moles of hydrogen. Okay, I did, I calculated the amount of moles of carbon I have. I calculated the amount of moles of hydrogen I have. Why can't I do the same thing for oxygen, right? Why can't we just take the amount of CO2 and the amount of oxygen in H2O? I plop that down, I find the amount of moles of hydrogen there, and then everything will be well. And the problem with doing that is, remember that this is a chemical reaction where it's a combustion reaction. So we're going to have, remember that in a combustion reaction, in this case, we're going to have our whatever mysterious compound that we have. This is going to react with oxygen, and this is going to produce CO2 and water, right? Whatever amount of hydrogen that we have is going to be the amount of hydrogen in the water, right? Because that's the only compound with the H in it. Whatever amount of carbon that we have is going to be the same amount of carbon in CO2 because, well, there's only 1 carbon in the CO2, right? But the problem with doing the same thing for oxygen is that when all of this reacts right over here, and we're trying to find out how much oxygen is in CO2, we don't know how much of that oxygen actually came from the original compound, right? Some of the oxygen might have come from the oxygen in the air that you used to react with. So doing this step would result in, error because, well, we don't know. We were not given enough information for that. But we do know that the original sample weighed 1.50 grams. And this is important because now what we can do is we can convert the moles of carbon, right? Recall that carbon has a molar mass of, I'm pretty sure, 12 grams, 1 mole. So in 1 mole of carbon, that weighs 12 grams. So that means that if we have 0.075 moles of carbon, we're going to have 0.9 grams of carbon. And likewise, we do the same thing for hydrogen. So we're just going to have 0.15 grams of hydrogen. Now, what we do is we take the total amount of grams that the compound weighs. So we know that this compound weighs 1.50 grams. So if we know that carbon makes up 0.9 grams and the hydrogen makes up 0.15 grams of all of this, that means that oxygen has to make up, and then subtract this. So that means that oxygen has to make up 0.45 grams of this compound, right? And now what we do is now we can, just oxygen. And now what we can do is now we can just convert this back into moles. So grams of oxygen, you could say that for every 16 grams of oxygen, that's the same thing as 1 mole. So do that. We're going to get 0.028125 moles of oxygen. Okay, so here's what we have. We know that we have 0.075 moles of carbon. We know that we have 0.15 moles of hydrogen. Now, what I'm going to do now is I'm just going to divide each one of these numbers by the smallest amount of moles I have. So notice how the least amount of moles I have is oxygen, right? I have the least moles of oxygen. That means that I'm going to divide every number by 0.028125. All right, I'm going to divide every number by this. So if I divide this by itself, I'm just going to have 1 oxygen. If I divide 0.15 by 0.028125, I'm going to get 5.333 repeating. And then if I do the same for carbon, 125, I'm going to get 2.66666 repeating. Okay, so that means that in our original compound, we have 2.66666 repeating amounts of carbon. For the amount of hydrogen that we have 5.33333 repeating. Actually, it might be easier if I just write 2 2/3. So I have 2 2/3 of carbon. I have 5 1/3 hydrogen, and I have 1 mole of oxygen. Do you see a problem with writing my compound this way? The empirical formula, when you're writing out the empirical formula, everything should be whole numbers. So in order for me to get everything to be a whole number, I'm going to multiply this whole thing by 3. All right, I'm just going to multiply the amount of everything by 3. All right, so now if I multiply 2 2/3 by 3, I'm going to get I should get 8, right? If I multiply 5 1/3 by 3, I should get 16. And if I multiply 1 by 3, I should get 3. And that is the empirical formula. This is the empirical formula. Sorry guys, I meant to put a 480 grams per mole there. Sorry. But pretty much, recall that the empirical formula is like the simplified version, right? And the molecular formula is sort of like the not simplified version, right? Molecular formula. So once again, I'm going to use the example for glucose. Glucose, this is the molecular formula for it. And then this is going to be the empirical formula for it. Now, of course, if you calculate the molar mass for the empirical formula, it's going to be lighter than the molecular formula for glucose, right? So in this case, right? In this case, what we're going to do is we're going to calculate the molar mass for our empirical formula. And let's see what we find out. 160 grams per mole. So if I have 1 mole of this is going to weigh 160 grams. Notice how the molar mass for this weighs 480 grams per mole. Now, if I divide 480 by 160, I'm going to get 3, right? And that essentially means that whatever the molecular formula for this, right? Whatever molecular formula that we have of this is going to weigh 3 times as much as what we have right over here. And if it weighs 3 times as much, that means we must have 3 times the amount of everything in our empirical formula. So right over here, what I'm going to do is I'm going to take our empirical formula and we're going to multiply it by 3, right? If it weighs, in this case, if this thing weighs 3 times as much, it must have 3 times the amount of carbon, 3 times the amount of hydrogen, and 3 times the amount of oxygen, right? So this is going to be C24, H48, and O9.